Hi guys, welcome to my channel. In this video we are going to solve a question about the reinforced concrete column, and the question will be determining the interaction diagram of the column. Now you can see on the screen. So this is the section of the column that we are going to solve now, and let's solve the question. But before we solve the question, if you like these videos, if you want to see more of the videos, please subscribe and share with your friends. Anything you wish, you can specify on the comments. I'm going to try to do my best. So now let's solve the question. First, I'm going to specify the pure axial force, and it calls an NOR. So it's going to be calculated as 0.85 multiplied design strength of concrete and multiplied the area of the section. Sorry, yes, area of section plus total area of the steel multiplied the design strength of steel. So let's apply the formulation. 0.85 multiplied 0.011. Look at here. Design strength of concrete. I'm going to divide 1000 to obtain as unit of kilonewton. Okay, 300 multiplied 500 plus total steel area. Look at here. This is the total steel area, 1600, and multiply the FYD as, look at here, is 0.365. So from this formulation, I'm going to obtain 1986 kilonewton as the axial force, and when the moment is zero. Okay, when moment is zero. So now I guess we complete first part. So let's start to calculate for the balance case. And I'm gonna tell you something for this question. In this question, we are going to assume the neutral axis values, and due to these values, we are going to obtain the axial forces and also moments. Then we are going to draw the interaction diagram. Okay. So now I'm going to solve the balance case. Due to balance case, I'm going to use the strain diagram of the balance case. This one. Okay, for the balanced. So for balanced, I'm going to write an equilibrium like that. Look at here. This is going to be a compatibility, and 0.003 multiplied d over d over epsilon sy plus epsilon cu. Okay, and let's apply the formulation. 0.003 multiplied d. What is d? Look at here. I'm going to show you on the question. So in this question, d is 500 minus 35 is equal to 465, right? And it's going to be millimeter. So let's apply it over 0.001825 plus 0.003, and from this compatibility I'm going to obtain 289 millimeter as the balance neutral axis. Okay, so now I'm going to calculate the strains, and then I'm going to calculate the stresses. So for the first steel, it's going to be something like that. Look at here, 0.003 and multiplied 176 over 289, and it's going to be equal to 0.001826. Now you can see that this is greater than epsilon sy equal to 0.001825. So it has yielded, and the stress at the first steel is going to be equal to 365 megapascal. Okay, so now look at here how I defined it. I'm going to take the length, okay, the distance above the neutral axis. Look at here. For example, for the first one, what is the length from the neutral axis to the steel? We are going to take the distance from the neutral axis to the steel. For example, this one is 39, okay, and for example this one is 254, and this one is 176. So I calculated for the first steel, then I'm going to do it for the second one. So let's do it. For the second one, it's going to be this one, 0.003. This is the strain of concrete, okay? So it's going to be 39. I told you that it's 39, if you remember. And this is going to be equal to 0.0000405, and this is smaller than epsilon sy equal to 0.001825. So we are going to calculate. So the stress, I'm going to show you the stress at the second, at the second steel. It's going to be the modulus of elasticity multiplied the strain of the steel. Okay, so what is that? 200,000 multiplied, look at here, this one is the strain of the steel, so it's going to be 0.0000405, and it's going to be equal to 81 megapascal. Okay, so now let's do it for the third steel. And the strain of the concrete multiplied, let's check what is the distance. Okay, so look at here, for the third one, the distance 254. Okay, I told you that it's going to be above the neutral axis. This one is the neutral axis, but it's going to be from the neutral axis to the steel point. So, and this is 254 over 289, and this is going to be equal to 0.0000264. Okay, and this is greater than epsilon sy, and it's equal to 0.001825. So the stress is going to be equal to 200. So for third one, it's going to be 265 megapascal. Okay, now we got the stresses, so let's calculate the forces. If you remember, the force is, so force S1, the area of steel, okay, the multiplied area, the area of steel multiplied the stress, and we are going to obtain the force. So let's do it. So for now, what is the area of steel at FS1? At FS1 is 600, right? 600 millimeters squared multiplied, what is the value of the stress at the first steel? Is 265, so it's going to be 0.365. I'm going to divide 1,000 to get as the kilonewton. Okay, so now this is going to be equal to minus 219 kilonewton. So y minus, I'm going to show you that y minus actually it is this above the neutral axis. Above the neutral axis is compression, but the below the neutral axis is tension. Okay, now we can see, I show you that below here, here is compression and here is tension. So the compression is positive and tension is negative. We are assigned like that. So let's do it for the second steel. It's going to be FS2 equal to, let's check what is the area. Area was 400 millimeter square, and multiply the stress of the steel is 81 megapascal, so 0.81, so 0.081, and this is going to be equal to 32.4 kilonewton as the compression force. So let's do it for the third one. This is also be 600, you know that the area of that, so let's multiply it with the stress of that. And this is positive 219 kilonewtons. Okay, now we obtain the forces. Let's calculate the, look at here, we have another force here. We calculate this one, this, and this. So here we have to calculate also for the concrete force. So concrete force, how it's going to be calculated. Let's do it. For the concrete force, it's going to be 0.85 multiplied the design strength of concrete and multiplied A and multiplied B. Okay, so 0.85, let's apply it. 0.85 multiplied design strength of concrete 0.011. This conversion just for the units, okay? So, and multiplied A, what is A? Let's check what is A. 246, but sorry, I forgot to write here. I'm really sorry. 289. I'm going to show you A. Is it multiplied the K1? If you remember, this is C, and 0.85, and this is K1, okay? And it's going to be equal to 246 millimeter as the value of A. I'm really sorry, but it's written here. I wrote it on the sketch. So this is going to be 246, yeah, right? And multiply 300, and this is going to be equal to 690 or 3 kilonewton. Now you can see that we got also F concrete. So let's determine the actual force. Okay, the actual force was total FSI plus also F concrete. So now we have all forces you can see on the screen. So let's do this equilibrium. It's going to be minus 290 plus 290 kilonewton and plus 32.4 and also plus 690.03, sorry, yeah, 0.03. So result of that is going to be equal to 721 kilonewton as the actual force. Now we got the actual force. Let's calculate also for the moment, but we are going to take the moment respect to centroid, okay? Moment respect to centroid. So let's do it. How the moment will be taken? So moment, let's show you the shape, okay? I'm going to take the moment respect to centroid, and for example, this is, I'm going to show you on this shape, this is 500, okay? 500. But it's going to be the half of this shape. It's going to be 250. So it's going to be, maybe it's going to be this one, 250, okay? 250. I'm going to take the moment respect to that point. So let's do it. This is going to be 215. The distance of the first steel and the third steel respect to centroid, okay? And multiply 2 because they are 2. I'm just going to write above them. And 219 plus 290, sorry, 690 multiplied 250 minus A over 2. A over 2, 246, right? Over 2. And I'm going to obtain as 182 kilonewton meter as the moment. So now I'm going to show you that why I just multiplied this both, okay? So let's do it. So look at here. This is the top steel, and this is the this is the top steel, and this is the bottom steel. Okay, so bottom steel it is at this point, okay, at this point, and the top steel is at this point. So the distance to the center of the cross section is the same. Look at here, 215 and 215. So I multiplied them. As 250 multiplied 2 multiplied 219 and plus 690. This is F concrete. Look at here, F concrete. The F concrete is going to affect at the midpoint of this concrete block, okay, at the midpoint of that. So when I applied at the midpoint of this one, and I'm take the moment respect to the midpoint of the cross section, I'm going to look at it. This is going to be 250, okay. This is 250. So I have to take the half of this because it's going to be the moment arm to here. Moment arm for FC, okay? Moment, sorry, yeah, moment arm. So now I guess you understand why I multiplied 690 multiplied 250 minus 246 over 2. So I guess you remember that I told you that we are going to make assumptions about the neutral axis, okay? The neutral axis. We are going to make assumption. So now assumption is here is C is equal to 600, and the A is going to be equal to K1. Sorry, yeah, K1 multiplied C, 0.85 multiplied 600, and this is going to be equal to 510. But you can see that the cross section is 500 millimeter as the height of the cross section, so it cannot be greater than 500. So I have to take as 500. Okay. So now let's do it. I'm going to first specify the strains I calculated before for the balance case. So let's calculate them here. Epsilon S1. Now you know what is the length of neutral axis. This is neutral axis. I'm gonna write here this is neutral axis. Okay, and this is, it's going to be as center of gravity. So now look at here. I told you that we are going to take the distance from the neutral axis to the steel, okay? From the neutral axis to the steel. So let's look at here. This is 600, this is 500. Until that point is 500. From here to this point, it's going to be 500, and this one is 100, right? This one is 100, if you remember. So let's check it. 0.03 multiplied 135 over the C value, and this is equal to 0.0675. It is smaller than epsilon sy is equal to 0.01825. So I'm going to calculate the stress, the stress of the steel. If you remember that it is epsilon modulus of elasticity multiplied the strain of the steel. So it's going to be calculated like that. 200,000 multiplied 0.00675, and this is going to be equal to 135 megapascal. Okay, so now let's do it for the the second steel. Sorry, yeah, for the second steel. 0.003 multiplied this length. What is this length? Let's check for, what is it for the epsilon S2? Look at here, 250. Okay, because you know that here is 215 and here is 35 and here is 100, so it's going to be above the neutral axis. So it's going to be 250 over 600 and multiply. Sorry, no. Sorry, I got confused. And this is going to be equal to 0.0075. Okay, 0.0070. Yeah, 175. So, and this is, look at here, this is smaller than epsilon sy is equal to 0.001825. So I have to calculate the stresses of stress for the steel. So it's going to be 175 multiplied 200,000, the modulus of elasticity for this steel that's going to be used, and this is going to be 350 megapascal as the stress. So let's do it for the third steel. Okay, so for the third steel, it's going to be, look at here, what is the distance? Yeah, I'm going to take from the neutral axis to the steel, the point of steel. So it's going to be 565, right? 0.003 multiplied 565 over 600, and this is equal to 0.002825, and this is greater than epsilon sy, 0.001825. So I'm going to use as stress equal to 365 megapascal. So now we got all the stresses. So let's calculate the forces. Okay, forces. I'm gonna write like here, forces. And for forces, Fs1, 600 the area of the steel multiplied stresses in the steel. So let's check what is that. 135, right? 135, but I'm going to divide 100, so divide 1000 to get at the kilonewton as unit. So this is going to be equal to 81 kilonewton. So let's do it for FS2, and this is going to be 400 the area of the steel, and multiply the stress of the inside the steel. It is 0.350, and this is going to be equal to 140 kilonewton. And FS3 is going to be equal to 600, the same area with the FS1, multiplied the stress. It's going to be 0.365, and it's going to be equal to 290 kilonewton. Okay, so now let's check the positive, being a positive and negative. Look at here, you can see that the all three steels are in the compression zone, okay, above the neutral axis, so they are all positive. Okay, these are all positive. So I'm going to now calculate also for the F concrete. Look at here, I'm going to show you. Now I have these three force, so let's also calculate the F concrete. F concrete is going to be calculated 0.85 multiplied design strength of concrete multiplied B and multiplied A. Okay, so it's going to be 0.85 multiplied 0.011 multiplied B 300 and multiplied A as 500. So this is going to be equal to 1402 kilonewton. Now you can see we obtain also the F concrete. So let's calculate the axial force. It is equal to total F steel plus F concrete, right? The formulation is like this. So because look at here, we have to have an equilibrium. We have an axial force here. Okay, so due to equilibrium, I'm going to have the summation of this side, and it's going to be equal to that side. So 81 plus 140 plus 219 and plus 1402, and this is going to be equal to 1842 kilonewton. Now we obtain action force. Let's calculate the moment for these forces. So I'm gonna show you that the moment, if you remember that I told you that at the previous example, it's going to be taken respect to the midpoint. Okay, this is midpoint. Now I show you that this force cannot create any moments, and also this force cannot create any moment, because F concrete, it affects at the midpoint of this cross section. So there's going to be just the moment created by this and by this force. Okay, these two forces, this is going to create at the moment. So now let's write the moment equation. 215, it is the same distance from the top steel and the bottom steel respect to the midpoint. Okay, so it's going to be 219 minus the force of bottom steel. Okay, 81. This is the moment arm, and this is the force. Okay, so now I guess I don't need to calculate to write other forces, but I'm going to write for you to understand that 140 multiplied 0, okay, and plus 1402 multiplied 250 minus 250, if you remember, okay, and it's going to be equal to 30 kilonewton meter as the moment. So now this part is also okay. Let's make another assume and solve it also.